Hello. Okay. So I think I'll get started. So my name is Grzegorz Kosakowski. I work for Typesafe. I'm part of Scala team. And today I'll be talking about how we go about making Scala. This will be kind of high-level talk about how we decide on what kind of features to work on what schedule, how do we ship those features to users, how do we test, how do we, what kind of tools we use to help us make sure that what you get as the end product is of good quality, so you can rely from the first release. And yes, basically how can we raise the bar of quality in Scala project. So the plan for the talk is I'll explain why do we make Scala. I'll try to kind of drill into this question, like why do we wake up in the morning and go hack on a Scala compiler. Then I'll touch on how do we go about new features. It's how many of those new features we should have, when do we want to work on them, and how we prioritize, and how do we deliver them to users. I'll spend more time on also on practices and tools we use. So like once we decided on the features we want to work on, it's like how do we actually do that, and what kind of tools support we have to help us achieve that. And at the end I'll show you who's making Scala, who's working on Scala these days, and how has this changed over the past few years, whether there was any change in kind of demographics of people contributing to Scala. So the first part, why do we make Scala, is actually the most subjective, and I think I will be mostly talking about my own personal motivation, but I think it at least partially reflects other team members' perspective on this as well. So the motivation for working in Scala is actually just one word. It's impact, and it's impact on the programming world in general, like the programming community. So, you know, like the thing that I'm really proud of working on a programming language is, you know, I can think of where we were 3 or 5 years ago and say, oh, you know, I put that work in the compiler, and I don't know, 100,000 programmers in the world are now benefiting from that work, and they go about creating their piece of software in a different way, probably better way. They feel better about programming because of Scala. So, and that's how I think about kind of the deep reason why I like to work on Scala is it's okay, what's the impact on people's lives, on programmers' lives, and whether that's positive impact. That's basically kind of the main question. So the goal is you want to maximize positive impact on programming world. But how do you do that? This is like very abstract. So you can decompose impact into like 2 dimensions. One is novelty. So this is about how innovative you are with your programming language. It's like whether you bring some new ideas to the table, and whether, like, for example, functional programming used to be a fairly niche idea. It was like popular in the academic world, but not so much in the industry. Object orientation was like dominant approach. So if you bring functional programming to the masses, that's like the novel idea you are spreading, and similar for things we do these days, like meta programming, like macros, and maybe, you know, improvements to macros over what other languages offer. That's all novelty, and you can be in different places of the novelty scale. Like you can be a little bit innovative, or you can be far out there, I don't know, exploring logic programming or things like that. So that's the one scale. And the other scale is popularity. So it's basically a question: how many people are using what you work on? Like how many users Scala has or any other programming has? And so novelty is the difference, the delta in singles programmer's life. Like, okay, whether he can say, yes, I'm doing something fresh, new here by using this language. And then popularity is how many people are feeling like that. And if you take a product of that, multiply those two numbers, whether novelty is actually really hard to quantify, but like intuitively can think of that there is some measure for that, then that's your overall impact. So it has two components. And one example of approaching this, like where do you put yourself on this scale, is programming language which is very novel, very innovative. Those are like probably research programming languages, like things people do when they work on their PhDs. So they're very far out there on the novelty scale, but on the popularity scale they're very small. So it's, there are actually a lot of languages where they have just few users, and there'll be like people from their research lab. Nobody ever in the world hears about this language. They explore really interesting ideas, but just nobody is affected in that. And the overall impact is very small. The overall impact is the area of your rectangle here. It's small impact. So that's one way of kind of positioning yourself on this graph. The other way is you aim for really high popularity, but you don't really explore or bring new ideas to the table. So you, like when you aim for high popularity, you probably don't want to deviate from what's already there. That's how you're easy to learn. So the programming language is, I don't know, has a syntax very similar to C. Family of languages will probably be very popular because it's very easy to learn. And you have programming languages like, I don't know, CoffeeScript, which is very easy to pick up, but it's very thin layer over what's available in JavaScript, so it's not very novel. And so this is like medium impact, and I would argue that most of mainstream languages are kind of in the, like the rectangle looks for them like that, so they're fairly popular or very popular, but they don't bring new ideas that often. So the holy grail, in my opinion, that's what motivates me, is this kind of picture. It's like you want a lot of innovation, you want people to feel like they're empowered to do their work better by using the programming language, and there's a lot of those people in the world. So it's a product of your, result of your work is popular, and that's large impact. That's like the thing you really want to aim is like you reflect back and you say, you know, I work on something which was really cool, and at the same time it affected a lot of people in a positive way. And it's so one problem with this graph is that popularity is a very it's a result. It's like, it's a measure, but it's a result of some other actions. And there is a lot of components that go into popularity that affect popularity. So, you know, like your platform might become popular, and that's how the programming language becomes popular. That's what happened to Objective-C or JavaScript, is that there is a lot of devices that you can deploy your code on, and that's the main driver for popularity. But me as an engineer working on a compiler, I don't really have much of a control over platform. I might pick different platform to kind of target, but in general I don't really have much of a control of a platform. There are other things that increase popularity, like writing a book on the programming language, like a very good teaching book might help with popularity, like increasing popularity. But as an engineer, I kind of would like to reduce the scope. So one really important component of that affects popularity is stability. Like if the platform, the language you work on is not stable enough, the common thinking is that you will reach some hard limit on how popular you can get. And stability is much easier problem to think of. It's easier to define, and it becomes an engineering problem, so it's easier to optimize for it. So the idea is you want to be novel and you want to be stable at the same time, and still achieve the large impact. And it's not very clear whether you can do that. Like if you look at many programming languages, they usually at some point stagnate, so they are moving to the left on the novelty scale, and then they just focus on stability. And kind of common wisdom is it's probably really hard to have both. So in a way, the area in your rectangle is fixed, and you just can pick your dimension. So people say stability is really important, and especially in business context. You hear this a lot. So when I joined Typesafe, I've heard this like number of times, but nobody actually explained why. Like why stability is that really important. People intuitively understand it. It's like things that are working should not break. That's kind of like a very informal definition of stability, like just don't break the things that are already working. But still, I kind of wanted to dig more into this, and there is a very interesting phenomenon described in economics, and it's called loss aversion. And the idea is very simple. It's like, imagine I give you $200, like $200 I just give you for free. You go home really happy, you just got $200. But on the way to home, you lose $100. So you get home and you realize, oh, I lost, half of the money I got for free as a gift today, and you get really upset about this. Like you are now happy, even though objectively speaking, and you're less happy than you were before you got $200. And that's, like, objectively speaking, it doesn't make sense. Like, you're still $100 more than before you got $200. But people, they feel differently about gains and losses. So there is this asymmetry where losses are seen as much more psychologically, people think that loss is much more affecting them and much more important. So the idea here is that in a programming context, it's like if you build something and it works, you get emotionally attached to the fact that it works, and also you base your other decisions on this investment. And if that breaks, like, you get really upset, and that's basically the loss aversion effect at play. So that's why stability is really important. People in the community who don't say stability is important is probably have not invested a lot of effort into building some products based on our platform, and that's why they have like smaller projects where they can easily adapt to whatever is happening. So the rest of the talk will be about how do we go about this holy grail, like features and stability, whether we actually have any answer for that or not. So before I dive into some of the thoughts we had, I want to recall the conversation or like a general mood when I was in when I joined Typesafe 2.5 years ago and I moved to San Francisco. I remember having a coffee with Adrian Moores, who joined Typesafe at roughly the same time as me, and he became my boss, and we were talking about this pressure on stability, on slowing down progress in Scala, and on one hand we understood why we need to do that. That's why Typesafe was founded. Essentially, it's like we really want to make Scala successful at large scale. But on the other hand, I was coming EPFL and from open source world as well. And I was thinking, okay, so is this all I need to do? Like looking 5 years back, like if people ask me what I did, it's like, oh yeah, I slowed down Scala development. Yeah, that's all I did. And that made me really sad. It's like I wasn't really sure about the job at the time. So we were really thinking hard about this, like how can we kind of reconcile two priorities, like keep Scala evolving and at the same time make it successful at the really large organizations. And there were a lot of people saying, like, you know, probably what will happen is we'll follow the path of mainstream languages, like we'll dumb down Scala at some point and just, yeah, slow down and to the point of like, you know, becoming really, really boring at some point. So now I will, so when you think about the novelty scale, it's all about features. That's like kind of your delivery vehicle of new ideas. Like you make some new features in the compiler or in a library, you implement it, deliver to users. So we got some data on like how much time does it take to develop a new feature. For a dedicated experienced compiler engineer, it takes around 12 months to develop a new feature. A new feature would be like something like, I don't know, value classes or in 2.10 agent re-implemented pattern matcher like from scratch to be more performant, more predictable, and get rid of a long list of bugs. And it took him roughly 12 months from initial prototype to something that we're confident we can deliver to our users. And he was very experienced in hacking on the compiler. But I also analyzed features like quasi-quotes, quasi-quotations that we delivered in 2.11, and many other features, and also the features we are working on right now, which I'll mention later in the talk. It's always roughly the same amount of time. You need 12 months of full-time, like really dedicated effort. So it's actually not a short time, like 12 months, like a whole year spent on a single feature. So that's one data point. Then the other thing that is really important is like you need feedback from existing projects. This is especially important for things like, you know, rewrites, like the pattern matcher re-implementation. No matter how good you are, you'll be making mistakes, and the feedback from real-world code or large code bases is really essential. And good design is achieved best by like going through a couple of failed iterations. It's kind of like with any other engineering, it's probably like that, but we are no exception. It's not here we can sit down and really focus and come up with a perfect spec and then go and implement it without trying a few iterations. Not like that. So you really need to try things out. Then once you develop the feature, the other question is like, how do you go about releasing it? And here, as we grew in the size of the community and number of our users, one thing we had to really understand is that our audience became much bigger and much more diverse than before. So it used to be that Scala was very small, and if you develop a new feature, everybody was interested in trying it out immediately. So it didn't make sense to, like, you just merge it, ship it to users. If it was of like and not such a great quality, people didn't mind it. They were still very excited about trying it out, reporting bugs and all that. So it's like, you know, in this picture, it's like you see a lot of people waiting for something coming from the air. But you see like this guy in the middle who is actually not really paying attention. He's not interested. And that's more of what we observe right now, is like there's actually ever-growing group of people who treat Scala purely as a tool to get their job done, and they benefit from the excitement of the other people, like early adopters, but they are not interested in testing very early prototypes and hashing out all the bugs. So the insight we had is we really have to segment our audience and make feature an opt-in initially. So what we do these days is we have feature flags. So every new major feature we develop, we merge into minor release. So the like 2.11, 5, 6, 7. Those minor releases actually get shipped with really large changes, but by default they are disabled and you have to opt in to try them out. And the examples are whole new backend bytecode emitter, like essentially 20% of the compiler is being re-implemented right now. We want to have a completely new backend in Scala 2.12, and you can slowly, like piece by piece, we merge this in 2.11, but it's disabled, and you have to use a special flag to enable that. Same goes for Lambda translation. Like we basically overhaul the whole pipeline internally, how we translate lambdas and how we process them internally in the compiler. This is in preparation for Java 8 style of translating, emitting lambdas in the bytecode. And internally, it's a big refactoring. And again, if you want to try this out, you opt in. Same goes for functional interfaces. Here we're using a little bit of an old style flag. So we used to have just one flag called X experimental, and that would enable everything that's experimental. But as you can see, we started using dedicated flags, and the reason is that very often one feature is broken, but the other feature is not broken, and we still like to have a feedback on this feature which is not broken. So you don't want to bundle too many things which are experimental under one flag. So we are working new optimizer. You also can enable it. Then the Lambda bytecode depends on the Lambda translation. It kind of implies it. You enable with target flag and so on. It's like we have many different ways to enable features we work on, and people who are really excited or really care about this particular feature, for example, class path handling reduces memory consumption, and for some people this is really important. They would like to get their hands on as quickly as possible, so they don't have to wait till Scala 2.12, but majority of people is not affected by the bugs in class path handling. So that's something new, and this wasn't the case before Scala 2.11. In Scala 2.10 was still this release where we would like release everything at the same time without massive input from the community. Like the input we would get only when we make the final release, which I would argue is a little bit too late. You want first, this minority to try things at their own schedule, and when they hash out bugs, enable by default. So the idea is that all of that will become enabled by default in 2.12, and then we flip the default in a sense that you are able to opt out of any of those if you find a blocking bug. So that's how we are segmenting our audience, and that's how we are reducing the risk for your upgrade. The other insight we had early on is that tools are top priority, and this is approach like the exact quote is coming from a guy whose name is Yisheng Wang, and he was a director of engineering at Facebook between 2006 and 2009. He wrote a series of short blog posts, and I included a link to one of them about how he was thinking about engineering at Facebook. And he said, in one of those blog posts, he said tools are top priority, to the point that at Facebook the best engineers worked on tools, not on product, not on any other things, just on tools. And the reason is that like the idea here is you can be really, really effective if you have good tools, and the end result of your work can be of a really high quality. You can deliver it much faster if you are equipped with good tools. So I will go through a few tools. So one is GitHub. We love GitHub at Scala. We moved to GitHub in December 2011, so 4 years ago. The original motivation was we wanted to, we like working with GitHub ourselves. It was a convenient place to host our code. But also we like the idea of pull requests, which at the time was still pretty novel. Like these days, like it's like obvious to everybody. But at the time it was still novel. It was much better than sending patches over mailing list or attaching them into Jira issues. And we also wanted to become more open source. Like Scala was at this kind of transition, in this transitionary stage where it was still mostly developed at EPFL in Switzerland. The code was available. It was available under open source license, but contributing to Scala wasn't easy. And moving to GitHub was the first step towards opening up the project. And it worked very well. We actually got overwhelmed. I looked at the history of pull requests. We got overwhelmed like from the first day. We had like 10 pull requests open the day we moved to GitHub. And actually for a while, we had this problem of like we were not prepared with tools to handle the load of pull requests we were receiving. But overall, like we were very happy with the move to GitHub, and it's a nice problem to have that you have too many contributors contributing. So the other idea that kind of I want to touch on is shortening the feedback loop. And there are actually a lot of feedback loops in the development of Scala compiler. So it used to be a few years ago that we would work on some new feature and or maybe even, let's say, a bug fix that's like a smaller scope. We would include it in next major release because we thought like it's a bit risky. So we would schedule it for the next major release. So you develop, as a developer of Scala compiler, you work on this feature, you merge it, somebody reviews it, you merge it, and then it sits there for a number of months and nobody's testing it. Like nobody from Scala, larger Scala community is testing it. Then we go and start preparing next major release. We start with release candidates, and people are finally trying results of our hard work accumulated over months, and they report their regression. And very often we have no idea when, like they just say, oh, my code doesn't compile anymore, and that's the error, and we have no idea who caused the regression and why and when this happened. And even if we identify, we developed some tools for that to kind of quickly go over history and test different revisions of Scala compiler to figure out when the regression happened. The other problem was like nobody remembered details of the patch anymore, even if we identified the patch which was breaking this project. So you had to, go and ask the original author. The author might be on vacation, so somebody else has to take over. And basically, the problem was that the time between you made a change and you discovered the problem, that it's breaking something, was really long, and the cost of context switching was really high. So we identified this as like a major productivity problem when working on the Scala compiler, and we spent quite some time on figuring out ways to shorten the feedback loop like that. So we did a few things. One was We validate every change to the compiler automatically these days. So if you open a pull request on GitHub, we have a bot which validates your change, and it runs a bunch of like the unit tests and functional tests and some large integration tests. And the validator is impersonal, and this is, I mean two things by that. One is like it's not human anymore testing. It used to be that you actually had to download somebody's branch and try it on your machine. It was really time consuming and error prone. So there is a bot doing that. But there is other really interesting thing about this is that at the time we were implementing changes to how we run the project, EPFL was still very involved in Scala development, and what we were trying to do is kind of introduce really good engineering practices, but at the beginning they were upsetting people who were used to different style of development, that you could commit whatever you wanted at any time you wanted, and nobody was really checking that hard the quality of your work. So if we started insisting on certain bar, and there was like a person checking somebody else code, it quickly were becoming like a very personal debate on like, I'm judging your quality of your work here, and like I think you should try harder, and you know, it's like a lot of time spent on things that are very emotionally draining and not very productive. So if you can encode checks, like code review processes in some automatic fashion where it's a bot saying, oh, you did this wrong, that becomes impersonal, and introducing new quality standards to the project becomes much easier because it's not personal anymore. It's not like I'm attacking that person. You introduce some new standards regardless of anybody's work. So this is really important. This is like if you're trying to implement a new practices in a project, I found this as a very powerful idea to just make it impersonal. So that's how the pull request validation looks like these days. So as I mentioned, like every time you open pull request, each commit, every change ever made to Scala these days is validated, checked, and there are like a number of steps or a number of smaller jobs that we run. So what we do these days is like the first thing is we build a Scala compiler and publish it to some internal repository. It takes 40 minutes to do that. We integrate IDE, so that was like another major change we've made at some point, is that Eclipse IDE, the plugin, is very tightly coupled with the compiler. Internally it uses like live instance of a compiler, but it's a separate project, and it used to be that we would break IDE like all the time. We would release a new version of Scala, and IDE plugin wouldn't follow us in release schedule for like weeks because they were busy fixing regressions, and sometimes it turned out like, oh, you need another release of Scala because it broke IDE so much. That was very counterproductive. So what we did is we decided we will always build a new version of IDE for each commit ever made to Scala, just to make sure, and execute their tests to make sure we never break them. So they are always available for release whenever we need them. We also run our tests, as you can see, our tests take over an hour to run, so it's quite a lot of tests being run. I think right now we're at 7,000 different integration tests that we run. So this is being done for every change in the compiler. But I mean, that was a very good step, and the pull request validation was actually a direct response towards this problem we had when macros were developed, that we merged a big change and the compiler was broken for 2 weeks and nobody could understand why. And we learned our lesson, like, you know, the whole team was stuck, like nobody could do any work. So we learned our lessons, like we really don't want this to happen again, and we introduced pull request validation. But then we still were breaking people's code a lot, like during 2.10 release, even like the minor patch, like the minor releases, bug fix releases, they would fix certain amount of bugs and they would introduce another amount of bugs. And people were not happy about it. We were definitely not happy about this. And again, the feedback loop was too long. You would introduce a regression and it would take a few months for somebody to report. And very often it would be like tedious process of asking somebody for reproduction. They didn't know how to prepare a project for us, so it's easy for us to reproduce the bug. And there's a lot of time spent on things that we felt we might be able to automate. So internal at Typesafe, we started working on a tool called dbuild. That was developed by SBT team. And the idea is you have a tool that can do massive builds, coordinated massive builds of projects based on SBT. At least for now, maybe we'll be supporting other build tools. But you create a configuration file, you put a lot of projects inside, and you can have a single command to build all of those projects and execute their tests. And the nice thing about dbuild is that it lets you do this in programmatic fashion, so you can program against your config, you can control it with commands, and you can replace parts of your dependency graph. So for example, what we are doing with Scala is we take all those community projects, there are over 80 of them, and we have a config where we can replace Scala compiler by arbitrary version we want, and plug it in and get all of the projects to use that version of a Scala compiler. And the result is that we recompile over 1.5 million lines of code every night with the latest version of Scala compiler we're developing. So we take master or like some branch of Scala and we just run through all of those projects and we execute their tests. So not only we cover problems like, oh, this code doesn't compile anymore, but also we cover mistakes like we generate broken code which blows at runtime, and those are actually the worst kind of regressions in the compiler, because somebody might build a library based on buggy compiler, ship it to the world, and it's broken. Not a good thing. So yeah, dbuild is our answer to that and many other problems. I personally think this has been the biggest productivity gain we had in the last 2 years internally at Scala team for development of the compiler. And the reason is that this feedback loop that was used to be several months has been shortened to like 6 hours. So here you can see a screenshot of Jenkins instance that's running a number of jobs for community build. So you can see we are running it for against Scala.I'll branch. We run it against Scala.I'll with a few flags enabled for new backend, new optimizer, and a few other things. So kind of integration build. We test it against Java 8, like 2.11 branch. We test 2.11 branch against Java 9. Java, as you can see, the last time we built on Java 9 was 5 months ago. So Java 9 through Jigsaw project broke us rather, like, yeah, you can't even start the compiler now because of the modularization effort they've done and changes to the class path handling. But the point is, we know. like, we don't have time right now to work on this, but we understand it. It's like we are not surprised. And we also do a few other things. We are testing Scala.12 here. And it takes, like, if you look at the last column, it takes around 5.5, 6 hours to run the entire build, to build this 1.5 million lines of code. And that's so much better than what we used to have, where we would wait several months for feedback from all those projects covered in those jobs. And that enables us to even change our approach to work. It's like we are much more willing to take risks these days because we are not afraid. We can just go and test things immediately and see what's the effect of the feature we are working on. To show, to kind of illustrate like what kind of bugs we caught with the community build. So Lucas Ritz is working on the new optimizer. That's a really cool thing in Scala.12 we're doing. Optimizer and backend is overall, it's like 30% of the compiler. We're replacing it. And dbuild is helping us test this as we go and detects really tricky semantic bugs that manifest only at runtime. We had one bug where we inline too much and lose volatile flag on an accessor to some field, and that manifested in some failures of concurrency tests in Scala's stream, or some whatever project that was. But the point here is that we would never catch this during a code review process. It's like there's so many interactions with so many features in a language, in a VM, that you just can't figure it out. And so, but the community build did, and it was very, once we saw what's going on, it was very easy to fix. The same goes for like edge cases in translation to Java 8 style of lambdas. Again, it's like people put lambdas in very unexpected places, like, I don't know, super constructor calls, and you pass a lambda that captures over some parameters of a class. The details do not matter. The idea here is that you can't predict all the code patterns people have in their projects, but with a repository of 1.5 million lines of code, you actually get a pretty decent coverage, much better than what we used to have. And this is the most recent example. It's from last week. Adrian Morris was working on a neat performance optimization for matching on tuples, like pattern matching on tuples. And he decided to hack on this quickly, kind of summarize the work that has been done over a few months, like some experiments. And he decided to run an experiment himself. He just took his fork of Scala compiler and ran through community build. He discovered very weird interaction with tail call optimization. Again, we would never, as a compiler writer and a reviewer of Apache, would never think of pattern matching affecting tail call optimization, but it was detected very quickly by community build. So the point I'm trying to make with all those examples is it's tremendously helping us increasing quality of the work we do on the Scala compiler, and encourages us to be faster at working on new features because we have an excellent feedback tool. So I also want to talk a little bit about infrastructure. So actually, I won't be talking about reactive infrastructure. There is no reactive in this talk. I actually want to talk about resilient infrastructure. And the idea here is that we really wanted and needed an infrastructure which recovers cheaply and happily. So again, the story is that we used to have a infrastructure. How much time do I have? Like right now? Oh, okay, yeah. All right, so I'll skip the resilient infrastructure. I'll just say we re-implemented the whole testing infrastructure in Scala. That was, again, Adrian's work. So to recap, when we work on Scala, it's all about making a positive impact. And by positive impact, we mean two things. It's about novelty and making sure we're still fresh, and we still bring new ideas to the table. But also we achieve high stability. So you can bet big projects on us. The way we go about this is we really think tools are top priority, and we spend an enormous amount of time developing those tools, and that's one of the explanations why 2.11 was a fairly conservative release. It's like instead of working on features, we decided to work on tools to help us deliver more features of high quality in the future. And we are also really proud of Scala becoming an increasingly open project. I had to skip a few slides on that, but our community is growing. And one of the reasons is because we have a very good tooling, so contributing to Scala is much easier and less error-prone process than it used to be. Thank you very much for coming here. And I don't know if, I probably don't have time for questions. I will take like 3 questions and I'm for the whole day available. So I guess the mics are here, but the room might be.
Hi. Perfect. Hi. Thanks for the talks, really good. And I agree with the impact. I work for Oracle with Java, and it's sort of what brings me up in the morning as well, is sort of changing a lot of things for people. So I had one comment that might be interesting for you around flags. So we have had the same thing where sort of want to put some things out there, a bit experimental or new features that we sort of don't fully trust yet, but want people to try out. Is what people tend to do is they pick a flag and they stick with it. So any name change in flag or change in behavior what the flag does is really expensive. So what we have is we have a, I don't remember the exact name, it is basically unlock experimental features flag, which basically, it doesn't enable anything except it allows you to enable those experimental flags. So it allows you to add the flag and have the sort of the behavior and the name you want it to have later on. Because if you have a Y flag now that sort of enables the feature and then you change it to disable it, you're going to have a lot of early adopters that might be using it in production, and all of a sudden they're disabling the feature. So it's just something to think about.
That's a good point. Thanks. Yeah.
Yeah, we do a similar thing in JVM where we have the -xx colon plus minus, etc. But we remove the perm gem flag, and in 8 it's sort of the feature is not there, it doesn't do anything, and so it prints a warning, and in 9 we're going to remove the flag, but we basically need a 2-year period to remove the flag.
Yeah, we have a similar program. Yeah.
Hey, just a quick question. How do you test, or do you test the compiler performance and speed?
I guess how to answer that. Probably the honest answer is we don't at the moment, and that's one of the infrastructure pieces we are still missing. So we focus on correctness. We are fairly, because of the fact that we're fairly conservative, used to be fairly conservative when it comes to features, we really didn't have a pressing need for performance testing. Now that we're replacing 30% of compiler, like the whole backend, the need is actually much stronger, so probably we'll have to figure out some answer. But right now it's, we're just pray and hope we don't regress.
Thank you.
Yep. Yeah, so I mean, it's not like we haven't thought about this in the past. The problem is that you lose performance not by like one. Like if you lose performance by introducing a very apparent performance regression, that's probably easy to detect no matter what you do. Is whatever timer you put in will detect that. But historically what we experience is that we would have a lot of tiny performance regressions that would just add up to big performance regression, but not single change which introduce big slowdown. And we're talking about things like in the range of 2-3% of performance regression on each change, and they would accumulate, and over time you would get like 20-30%. So we tried to develop a performing testing framework for that, but the JIT non-determinism was, and GC non-determinism, but mostly JIT, was really making it hard. So basically the noise you get from JIT taking different optimization decisions was so high that we couldn't detect performance problems reliably. And that's where we got stuck. It's like we just can't detect those problems, so we didn't continue. We have some new thoughts on how to make JIT more predictable and then have a better confidence intervals in performance testing. But it's not trivial. It's like benchmarking as usual. It's not trivial. We're not in any better position. All right, so thanks again for coming to my talk. And if you want to chat about tools, or maybe you would like to be part of the community build, like this massive build, just come and talk to me afterwards.